Well, hello. Hope everybody's having a great time so far. My name is Afiq. Today, I'll be presenting about abstraction patterns for cross-platform development. So this is a topic that's very dear to my heart because when I was starting out, I was really struggling to find an abstraction pattern to abstract all of these platforms. So I had to experiment a lot and dive into a lot of large code bases to figure out how they were doing things. So, I would like to share my experience and hopefully it becomes a reference point for anyone who wants to start writing cross-platform code. We've got a lot covered, so let's dive straight into it. So these are the things that we will be covering today. I'll give you an introduction. I'll define what abstraction means. I'll tell you the different types of cross-platforms that exist, why you want to create an abstraction pattern, and also the challenges associated with it. And then we're going to go over using preprocessor macros to abstract our code and how it looks structurally in the code base. And then we're going to take a look at runtime polymorphism and how we can use runtime polymorphism to create our abstraction. For the first two, I'm not going to dive too much into it because it's pretty much standard practice in the industry. And then we're going to take a look at a slightly unconventional method, which is using the PIMPL idiom to create our abstraction. And then we'll see how we can use build systems to help us create the abstraction. And then for number 6, I'm just going to leave it out to the presentation because personally, I don't even have a name for that pattern. And then we'll talk about C++20 modules and how we can use C++20 modules to help us create an abstraction pattern. And then we're going to close it off with a conclusion. So without further ado, let's begin. Introduction. There's two definitions to abstraction. One is in English and one is in software engineering. In English, it originates from the word abstract, which is to dissociate from any specific instance. The definition in software engineering is a bit long, which is the process of removing or generalizing physical, spatial, or temporal details or attributes in the study of objects or systems to focus attention on details of greater importance. It is similar in nature to the process of generalizing. I just ripped that off for Wikipedia, so the TLDR, for me at least, is making code generic. Now, when we talk about cross-platform, it could mean several things, right? It can mean different operating systems. You're writing software for Linux, Mac, and Windows. It can also mean different APIs. The most renowned example for this would be video games, right? Most video games today support multiple rendering backends. The modern ones are DirectX 12 and Vulkan. It could also mean different hardwares. Right, you're writing a software for the desktop or embedded system. There are hardware constraints that needs to be taken off. And then the last part is cross-platform could also mean software. So another example of this would be in games, we have different storefronts that you can buy your games from. We have Steam, the Epic Games Store, and also the Microsoft Store. All of them provide functionalities such as rewarding an achievement if a player achieves something. They could message their friends or they can invite their friends into the same gaming session as they're playing in. So most games have an abstraction for all of these functionalities so that they can easily invoke the functionalities in each of those storefronts. As to why you want to create an abstraction pattern when dealing with cross-platform code, because when you have the abstraction, it provides the unified interface that exposes a single source of truth to the users of your library. It becomes easier to maintain because you no longer have code divergences outside of the library. And also, you save development costs in the long term. Yes, there is that initial upfront development costs, right, when you're doing the R&D and you're doing the planning. But over time, it saves a lot of development costs. And when you already have an abstraction for your cross-platform code, you pretty much enable new business opportunities because, let's say you want to support a different platform in the future, right? You already have the framework, you only need to extend it. Now, as all things software engineering, abstraction is generally difficult because you kind of require knowledge of all the platforms that you want to support. And it also takes a lot of planning. Not only that, it usually takes a while to strike a balance, even though most platforms functionally achieves the same thing, but they all have nuances that are unique to each of them. Some may take X more steps to do something, while some may take less. Now, before we dive into the first pattern, let me give you some context of what we'll be doing today. So as an example, let's say we are setting up a new shop, right? We are a new software shop. We provide rendering services, and we have to support multiple graphics backends. Upon launch, we need to have 2 backends, DirectX 12 and Vulkan, but possibly more in the future. So for each platform, we are going to create a graphics device that holds an instance of the API and whatever variables necessary to interact with the platform. We're going to add a few functions to that device so that users of the library can execute and interact with the GPU. And then we're going to discuss its structure, the pros, and its cons. A quick disclaimer, we will only touch the surface of how each feature works internally. There's not going to be there's not going to be a detailed discussion. So we're not going to have an in-depth explanation of C++20 modules. We're only going to use parts of the build system that we really need to help us create the abstraction pattern. So onto our first pattern, which is using a preprocessor macros. Arguably, it is the simplest method that you can use to abstract cross-platform code. In fact, I would say that it is probably the first method that any C++ engineers would use when they're starting out. And it works really well generally for small lines of code, right? Think between 1 to 3 lines. So this is how it would look like if you were to use preprocessor macros. Oh, it's a little bit too small, but can you guys see it? The code, okay, yeah. So notice that I've defined 2 preprocessors, use Vulkan and use DX12. And depending on which one is set, I include the header files that are required to interact with the platform. And with preprocessor macros, this is what the function body would look like. You would have different blocks of execution depending on which preprocessor is set. And this is actually pretty common of C libraries, right? Where, a C library that supports multiple platforms. So immediately when we look at this, we can immediately figure out the types of problem that we will be dealing with in the future. Basically, the function body can become really long. Some platforms take a lot of lines to initialize or execute something, and the more platforms you support, the more exponential the function body grows. At some point, it becomes impossible to read, right? Merging code becomes extremely difficult, harder than it already should be. And you get ugly code structure, there's macro pollution all over the place. But the most important part, for this to work, your preprocessor has to be exposed across all of the projects, right? You can't keep it defined within the library itself. So as a general rule of thumb, don't do this, right? There are better methods to abstract cross-platform code, which is what we'll be covering next, runtime polymorphism. So the basic idea of runtime polymorphism is that we have an abstract base class or a base class with virtual methods, and then we create an object that is derived from the base class, and then we fill in all of the implementation details by overriding the virtual methods. So a quick refresher on runtime polymorphism. When you declare a method as virtual, the compiler generates a vtable. A vtable is basically just a lookup table of function calls to resolve at runtime, and it exists for every single type of class that has the virtual specifier. Aside from that, the compiler also generates a virtual function pointer that points to the vtable of that class. So if you were to create if you could abstract cross-platform code with runtime polymorphism, it would look like this, right? Say I have a device, a HPP, that I have declared every single object and resource that I need from the platform. I've prefixed the objects with an I to denote that it's an interface. And then the choice that I went with is to declare the virtual methods as pure virtual so that nobody can instantiate an object of this class. And then notice down there, I have 2 factory functions that returns a pointer to that interface. And then for each platform that we are supporting, in a source file, we basically declare the implementation, and we derive the implementation from the interface, right? You can do that in a header file, but the thing about header files and how they work is that whatever you include gets exposed to right? It's transitive. So if you want to do it, if you want to declare the implementation in a header file, make sure that you have the dependencies sorted. But the choice that I went with is to declare them in a source file. And then for each method that we have, for each method in the interface, we override and fill it with the implementation details. And then notice the factory functions. We simply create an instance of the implementation and then return it as the interface. Now, with runtime polymorphism, it's a language feature, very easy to get started, right? When you use it, you pretty much have consistent. You can pretty much have a consistent interface, and you introduce non-divergent code paths outside of the library, right? Basically, what it means is that you can pass the object around as a pointer to the base class, and the virtual function pointer just takes care of the correct function call. In terms of merge conflict, it's not so painful because it is self-contained, encapsulated within its own source file. So you only have that file to deal with, and only that platform to deal with. The cause of runtime polymorphism is pretty much well known, right? We have the vtable lookup. You're missing out on inlining opportunities, and devirtualization might not happen. Hand wavy statement a little bit. Depends on how good your compiler implements devirtualization. But another problem is that your final executable also contains code of the other platform's implementation. Not to mention, if you would declare the implementation in a header file and you don't manage the dependencies correctly, right? The declarations from the platform can leak out, and also you get method duplication, right? You're declaring the virtual methods in the base class, you're declaring them again in the derived class, and then defining it again in the source file. So it's 2024, let's try something different. And the different thing that we're going to try is, we're going to create an abstraction for our cross-platform code with the PIMPL idiom. Now, PIMPL stands for pointer to implementation. The basic idea is that we hold a pointer to the implementation with a void pointer, or you could forward declare the implementation as a pointer, or if raw pointers are not your thing, then you could wrap it inside of a std unique pointer. But regardless of whichever method that you choose, we have to have the implementation be defined in a source file, and then we create an instance of the implementation. Then we take the pointer to point to that implementation. So this is how it will look like, right? This is our interface, which is a device. We have all of the methods over there. And then notice that in the private segment, we have a void pointer that will hold the will be the pointer to our implementation. But the use of void pointer is often not encouraged in the industry. So we're going to swap that out. We're going to use the forward declared implementation object instead. And then we're going to wrap it up in a std unique pointer to have its lifetime properly managed. Now, notice that there is no way for us to assign the pointer. We can introduce a new constructor in the public segment, but when we do that, it basically enables users of our library to, instantiate the object again, create the object again when it has already been constructed. So to avoid that, the choice that I went with is to declare the constructor in the private scope and introduce a friend function. And then for each platform, we introduce a source file, right? We put whatever variable we need inside of the implementation's definition, whatever variable we need inside of the structs body. You can change it into a class and put them as private, but there's really no need to, in my opinion, because it's self-contained. This struct is never going to be exposed outside of the library. It's only for internal use. So might as well keep it as a struct and have everything as public. And then for each method that's in the interface, we're going to use the same name for the implementation. Now, the reason for this is that so that when we assign the pointer, we can basically just call the method, right? We don't have to think about the different names that the implementation contains. So with each method, we give its own definition, and we're going to do the same thing again for the other platform. And then in the interface that we're going to expose to the users of our library, in the constructor, we're going to assign the pointer to the implementation. And then in each of the methods, we're simply going to call the implementation's version of the function. And then in the factory function, we simply create an instance of the implementation, initialize it. If it's successful, then we return an instance of the interface. If not, we return a std null. So the pros are you still get a self-contained implementation, right? Diffing and merging code, it does not become difficult. It is self-contained within its own source file. You still get the persistent interface regardless of the platform, same as runtime polymorphism, right? There are no compilation dependencies on the interface, only in the implementation. And you still get the consistent non-divergent code paths, which is basically the same thing as runtime polymorphism. But there are disadvantages to using PIMPL. You still get method duplication, which is the same problem that we had with runtime polymorphism. And there is a performance cost to it, right? Instead of a vtable, you now have a pointer indirection at every single function call. But the biggest problem is this doesn't work. Because we've used the same declaration for all of the implementation, right, for each platform, we've basically broken the one definition rule. Now, the one definition rule states that for every declaration, there can only be one definition. We can sort of fix this by giving different names to the declaration for each platform, but then we would have to use a std variant in the interface. And then in the methods of the interface, we would have to then decide, okay, what instance is the variant holding, and then call the correct function for it. So language feature-wise, we've pretty much hit a roadblock, right? There's nothing else in C++ that can help us solve this problem. And this is the moment where we start using tools. Enter the build system. Right, because programming language today is not just the syntax and the rules, development tools and dev environment is an integral part of a programming language. So the thing about build systems is that they provide a platform-independent method to configure and generate builds for a target platform. And they're a very intimidating thing, right? They're not really beginner-friendly. But I would argue that it's a natural process for C++ engineers to get involved with project configuration at some point in the career. It can be early or it can be late. But what do build systems actually do, right? They help us generate project and solution files. They define new presets. They alter the properties of the projects for different configuration. So that can mean different compiler flags, warnings, optimizations. They also enable us to include different include paths for each configuration. They also help with project structure in terms of file organization, right? I mainly use Visual Studio, and you could sort of organize your file in the Solution Explorer with CMake. And then this is the most important part. You can include or exclude source file based on the configuration. So what problems are left unsolved, right? Remember, we had the ODR violation when we were using the PIMPL idiom. When using runtime polymorphism, right, we had multiple platform implementations in the final executable. So the fix for this is actually really simple. We only need one implementation per configuration. And we can do that with build systems, right? The example I'm about to give is CMake because that is what I mostly use. So in our CMake presets.json, right, we do the usual stuff of some basic presets. And then for each platform that we're supporting, notice that in the cache variables, we have separate variables set, right? We have separate variables that are enabled. And then in CMake list.txt, we define the options, which defaults to off. And then for each option that is enabled, we basically include separate source files. Also, a note that you don't really need to include the header file as the target source, but because I mostly use Visual Studio, if you don't put it, it's not going to appear in the Solution Explorer. So that's the only reason why I include the header file in as a target source. So now that we've unlocked the power of a build system, can we implement a pattern that has no pointer in direction to reach the implementation and no vtable lookup? Well, the answer to this is yes, we can. So enter the mysterious pattern that I don't have a name for, but it is heavily inspired by CRTP, right? CRTP is basically you have a base class that has a template parameter. You create an object that is derived from the base class, and you just apply the object's name as part of the base class's template param. If all of that sounds gibberish, then basically, there's a visual representation. We have the base class that has a template parameter. We create a derived class from the base class, and then the derived class is part of the base class's template parameter. And with CRTP, you can abstract code like this, right? The benefit of CRTP is that we can cast the this pointer of the base class into the implementation and then invoke the derived class version of that function. You can't, if you're supporting multiple platforms, you can't really put all of the implementation details inside of the base class's method. So that's why we had to invoke the derived class version of the method. So for each platform, we simply create a derived class and then put the derived class's name as part of the base class's template param. But notice there is a problem, right? The device is the interface that we want to expose for our library, right? But the implementation's name is part of the interface. And we don't want that, right? We don't really want to expose all of the platform detail outside of our library, right? And there is also the problem of method duplication. Not really a big problem, but it would be nice if this wasn't a thing. So we have the build system now, right? We could define new build presets. For each preset, we can have separate include paths. We could also include or exclude certain source files for the target. And when we configure this correctly, right, it pretty much guarantees that we only have one platform for preset. And with that being said, right, the base class doesn't really need to be templated. Now, this is, as you can already figure out, this is pretty much a very hacky solution, which really relies on the build system. So what I've done is basically strip out the template from CRTP, right? It basically just becomes CRP. So how do we do the CRP? Well, again, with the CMake presets.json, we have the basic configuration, and then for each platform that we're supporting, we're basically just doing the same thing as before. And then folder structure-wise, for each platform that we're creating a subfolder for each platform that we're supporting with all those source files in the subfolders, right? You can do this for every single thing that you're trying to abstract. But personally, my personal preference is that for the header files that we want to expose as part of the library, we collate them into a single header file, and in this instance, just rhi.h. And then in CMake.txt, we have the usual options. They are defaulted to off. And then again, depending on which option is set to true, we include this we include the source files for it. So the way you would do this is that the base class, which acts as an interface, right, contains all of the platform agnostic information. You still have the methods that you want to expose as part of your library, right? You can include generic methods like the device name or driver version, right? When I say generic methods, I mean methods that you don't really need to call the API of the platform to retrieve. It could be some pre-computed value. And then for each platform that we're going to support, inside of its source file, we are going to declare the implementation for it by deriving from the interface, right? And again, it doesn't need to have any encapsulation because we're never going to expose this class outside of this object outside of the library, and having them as public just makes it easier, makes it more accessible. And then for the method of the interface, we simply cast a this pointer to its derived class, which gives us access to all of the variables that we need, and we can handle all of the platform-related logic in the method. Now, we can go one step further, right? Because sometimes objects, the different objects in a platform have dependencies between them, right? In the realm of graphics, say the swap train needs to know about the image. The command buffer needs to know about the buffer or the image that it's trying to process on. So we can go one step further and introduce a header file that collects all of the interface. Sorry, that collects all of the implementation details. So again, we have the implementation, derive, declare them, include whatever member variables that we need. And then basically, instead of, and then we include basically the header file, the collated header file in each of the CPP file instead. So now you're saying, this is all too hacky for me, right? Is there a more standard solution? Well, the standard solution would be C++ 20 modules, right? If you have access to C++ 20 modules, modules are the way, C++ 20 modules are basically the way that you would use to abstract cross-platform code. With modules, you have two new keywords. Well, not actually two. One is refurbished, the other one is new. Export, you basically attach it to a declaration and cause that declaration to become visible to module importers. And then import, basically you use it to import a module unit. And then there's two new properties that you need to be aware of: visibility and also reachability, right? When the declaration becomes visible, it's basically a candidate for a name lookup. And reachable, right? All the semantic properties for the declaration becomes available to the module importers. If you're interested to know more about C++ modules, right? There's a talk from Andreas Waste from last year's CPPCon, right? I highly recommend everyone to check it out if you're interested about modules. So with modules, this is how you would abstract cross-platform code, right? In the global module fragment, we basically include whatever header files we need from the platform. And this is okay because, with those two new properties, visibility and reachability, they are never going to leak outside of the module. And then we have the interface device that has all of the member functions that we want to expose, and then we keep all of the variables in the private scope. And we do that for every single object or resource that we want to expose from the platform.
Are these separate CPP files, separate HROPs, and I've never dealt with mocks at the moment, so I'm sure you might have about it.
Right. So what you would do is basically you would have, well, for modules, they're no longer CPP files. They are module interface units, right? And then a module interface unit is basically, if you're using MSVC, the extension would be IXX. If you're using MS-Build, it does everything for you automatically. I think in Clang, it's CPPM, and then G++ is CSX.
They're totally different files for different build systems, essentially, and they implement them differently. Is that Vulkan / RHI IFX, and then...
Okay, right. Right, okay. So basically, remember that we had the build system from before, that we had different subfolders, right? Different subfolders for each platform. You will basically have a file with the same name, but located in those two separate subfolders. And then because you can swap out the configuration, right? You can swap out the configuration. If you're using an IDE, it does the magical thing where the Solution Explorer gets updated to map to the correct files. But if you're using a build system, it knows how to properly manage which module to pull into the project.
It's not as simple if you're using different IDEs, such as one being Linux, one being in Visual Studio, one being in Android Studio, due to, let's say, using iOS standard.
Right, yeah. So the question is, it wouldn't be so simple if we were to be using different compiler. Well, that's the idea behind using the build system, right? Because the build system should manage everything for us. If you're using CMake, you actually don't need an IDE. No? All right, okay. Well, even if you're not using CMake, because I've used SharpMake as well. SharpMake is Ubisoft's proprietary build system, right? They should handle everything for you, right? As long as you're using a build system and it's set up correctly, hitting F5 compiles everything and it should do everything for you.
But local modules in your particular implementation just do it and it should just work, is the idea.
Sorry, could you repeat?
Local modules in your particular implementation and it should just work, is the idea of what it's essentially what I'm getting from this example. So modules, if they're in the build system, should just work. If the build system sees the module for your implementation.
Well, a module is really no different from a normal source file, right? Like, if you could do the same with a source file, you could pretty much do the same with modules. Yeah.
That's the thing I'm trying to get my head around.
Yeah.
They're not CPP files, but it's the implementation-specific version of way of doing it, but it's still a CPP file in spirit.
Yes. Right. Or hand wavy statement. Yeah. So, yep, we would then put all of the variables that we need inside of the preface segment. But let me just go back a little bit. But this doesn't really let us enforce a way to have that consistent interface, right? There's nothing that's stopping me from changing create swap chain to allocating swap chain for Vulkan, and then for DX12, I could just maintain create swap chain. So in order to provide that unified interface, what I would do instead is, going back to our runtime polymorphism example, right? We create an abstract class that has all the methods that we want to expose as pure virtual. We do the same for all of the resources. And then basically, that pretty much guarantees consistent interface. And then in our module, we simply derive all of the implementation from the abstract base class, override these methods with the implementation detail, and that pretty much guarantees us a consistent interface regardless of whatever platform we're choosing. Oh, yeah, I don't understand why there's two lines down there, but then, we're storing platform information inside of the private segment for the class. And, you probably remember that I've mentioned, sometimes there are dependencies between objects, like, there are dependencies between objects. For example, in graphics programming, when you're recording a command list, right, and you're binding a vertex buffer, it wants to know the handle for the buffer. So what should we do? Do we, declare a bunch of friend functions or friend classes? If you have an object that has a lot of dependencies, the friend list is going to be really, really long. Do we make them public? Well, if we put the member variables in the public scope, that basically makes the variable becomes visible outside of the module, and you basically leak out all of the platform information, right? Implementation. With getters, you pretty much get the same problem as making the variables public. You can disguise them as a void pointer. That's how thread native handle does it. But then you lose all the semantic meaning behind that variable. So what if I tell you that you can pretty much solve this problem by using CRTP minus the template, and you can do it with modules too. So in a module, right, that we want to expose as part of our library, we have the interface. This time, we swap out a little bit. We're not going to focus too much on the device because we've been doing that throughout the presentation. Let's just focus on the buffer for now. And then notice that I have two static functions. They're pretty much inspired by Rust traits, right? And then in each of the source file, well, I shouldn't say source file because in terms of modules, they are module implementation units. In each of the module implementation units, we create the implementation that's derived from the interface, and we just put all of the variables in the public scope, right? And then in the static function from, which is used to create an instance of the object, right? We create an instance of the implementation. That basically gives us access to whatever variable that it has, and then we return the implementation. And because of how inheritance work, it's going to be implicitly classed to the base class, which is the interface that we're exposing. But there is a problem, right? With the way how modules work, if you declare the implementation details in separate module implementation units, there really is no way to share visibility of all of these declarations. You can import the module in a header file. I don't know what that does because I've never done it before. But let's say if you can, and then you include the header file in the module implementation units, right? Personally, I don't think that would work. But yeah, there really is no way to share declarations across module implementation units other than forward declaring, right? So even modules themselves, it's not really a silver bullet. The only way that you can, the only method really that you can use is to forget the idea of having separate module implementation units for each object that you're trying to abstract, and collect them all inside one giant module implementation unit, so that all of the declaration becomes visible for all the objects. Right, so as conclusion, creating an abstraction pattern for cross-platform code is very hard, right? Every pattern has its unique problem. CR minus TP solve most of them. Modules are great, but can be tricky when dependencies exist because of how modules work with each implementation units and stuff. And in order to properly abstract cross-platform code, the usage of a build system is pretty much a must, right? So my advice is, if you're feeling bold, use the CRP method, right? If you're feeling a little bit conservative, use runtime polymorphism and build systems. That way you don't have other platforms implementation detail in the final executable. If you like the latest and greatest, use C++20 modules. So with that being said, we've pretty much covered all there is. I've discussed the use of preprocessors and how as a general rule of thumb, we shouldn't be using them. I've talked about runtime polymorphism and how we can use it to create the abstraction for cross-platform code. We've talked about the PIMPL idiom and how it's not really that different from using runtime polymorphism. We've also covered build systems and how we can use it to leverage parts of the build system to help us create the abstraction. I've introduced a technique that I personally use in my own personal projects, which is inspired by CRTP, but minus a template. And then we've talked about C++20 modules and how we can use them to solve problems with code abstraction. But with problems, but C++20 modules also have some problems by themselves. With that being said, thank you. I hope you enjoyed the presentation, and hopefully you learned a thing or two from this. Yeah.